All right, so let us start. Last time, this is where we start, right? So we, after talking about the supremum property and the infimum property, and then seeing the relationship between supremum and infimum, right? So for the existence of supremum and existence of infimum, we define the infinitesimal characterization of the supremum, right? So we say that U is a supremum if and only if U is greater or equal to x for all x in S, as well as it satisfies the other condition, that is for all epsilon positive, there exists an x naught belongs to S such that U minus epsilon is less than x. No, right? So that is what we did last time, or what we write last time. Okay, so now what we are going to do is we are going to prove this. So you can notice that this is actually a necessary and sufficient condition proof, right? So you have to prove if and only if. So basically you have to prove both ways. You assume U is a supremum, and then you have to show that it will satisfy the two conditions, and then you assume that both the conditions are satisfied, and then U is a supremum. Right? So you have to show that, right? So okay, so that's what we did. That's what we want to do. So here I'm going to go with the other part. So let us assume that for the proof. Okay, so we assume okay. So let us assume that the number U satisfies both the conditions, right? So we have to show that U is the supremum, right? So right, so this upper bound part is quite clear, right? So because U is greater or equal to X, that is what the statement 1 says. So therefore, it's obviously the U is then upper bound of the set S, right? So you know that. So now we have to show that it is the least upper bound, right? So that is what you have to do to prove that something is a upper bound, right? So in that case, you have to show that it is the least upper bound. So now let me say okay, so let us say U be any other upper bound. Sorry, V be any other upper bound. So we have to say that or show that V is the greater than U, right? U should be the smallest upper bound, right? So what is that? So less than equal to V. Right. So then, if you assume that, or if you take V be any other upper bound, then what you have to do is you have to show that U is less or equal to V. Okay. So again, I will show this by using a contradiction. Right. So let me assume that. Right. So let us assume that U is strictly greater than V, and then we can get a if we get a contradiction, then that is enough to show that U is less or equal to V. Okay, so in that case, and so if U is greater than V, then U minus V is greater than 0. You will know that, right? So you can take epsilon as u minus v, because statement number 2 says for every epsilon positive, right? So you can take a positive number as epsilon. So in this case, you can take u minus v as epsilon, right? So then so what 2 says is there exists x naught belongs to S such that u minus epsilon u minus v less than so, right? So in statement 2, you substitute u minus v for epsilon. So that is what you do. Okay, so once you do that, you can simply notice that this says there exists x naught belongs to S such that u minus v. So that's plus v. V is less than small v is less than x naught. But this cannot be true, because we say that v is an upper bound, but we say there exists an element in the set bigger than the upper bound, so that's not possible, right? This is the contradiction. Okay, so this one is a contradiction. This is a contradiction. Then what we assume here is not true. So hence so u is less or equal to v. So here we say that u is an upper bound, and for any other upper bound, we show that u is less or equal to v. Therefore, we can say that u is the least upper bound, or in other words, u is the supremum. That's supremum on S is equal to u. Okay. So here what we did is we proved this part, right? From 1 and 2, we are able to come back to supremum, right? So that is what we proved here. Assuming that 1 and 2 are true, and then we show that u is the supremum. Now we have to go the other way around, right? Now we have to take that u is the supremum of S, and then we have to show that 1 and 2 are true, right? Holds. Now we suppose that supremum of S is equal to u, right? And then we have to show that u is greater or equal to x for all x in S, and for every epsilon positive, this and this is true, right? So and because the second statement is true for all epsilon, right? So we have to start with an arbitrary epsilon. So let us take some epsilon positive as well. Right? Now we have to show that 1 and 2 are true, right? So let's do one by one. First part is simple. Right? Once you know u is the supremum, it is clear that U is the upper bound of S. Right? So therefore x is less or equal to U for all x in S. Right? Now what you have to do is you have to show the other relationship, right? The statement 2. Okay. So 1 is 2, right? So right. That's because of this 1 is 2. Now we have to go to the other one, 2. And so that's also not a big thing. Right? Right? Now you take arbitrary epsilon greater than 0. So U minus epsilon will be strictly less than U. So U minus epsilon is strictly less than U. You know that U is the least upper bound, right? You know the meaning of supremum? U is the least upper bound, right? So therefore, U minus epsilon cannot be an upper bound, right? It cannot be an upper bound because it is smaller than U. So in that case, we can see then there exists some x naught belongs to S such that U minus epsilon is equal to x naught, right? Because it is not an upper bound, so that means it is smaller than upper bound, so at least there will be one element, right? Such that is S equal to this. So in fact, we can say that because this not necessarily equal to this. You can always find something bigger than that. Right. So that's how you characterize the upper bound, right? By using an epsilon characterization, right? So some people say it as an epsilon characterization of supremum, right? But it's actually the infinitesimal characterization of a supremum, right? So if U is the supremum, then x is less or equal to U for all x in S, and for every epsilon positive, there exists x naught belongs to S such that U minus epsilon is less than x naught, right? The last sentence, since epsilon positive is arbitrary, for epsilon positive, there exists x naught belongs to S such that U minus epsilon is less than x naught. Hence, 2 ohms. Okay, so that's how we prove this, right? So because of this, we can see that the similar type of infinitesimal characterization works for the infimum as well. Right? So let us write down the infinitesimal characterization of infimum as Okay, so first let us look it as a picture. Right, so here is the line, and this is the set. So you know that. Okay, this is your L infimum, right? So obviously the first one is always same, right? Every element in the set is greater than or equal to infimum, right? Now the other one, the epsilon definition. So here you can see that you have to move this further from the infimum, right? So when you go here, right? So this becomes L plus epsilon, right? In the upper bound, you come below from the upper bound, so you have U minus epsilon. But when it comes to lower bound, right, you go higher than the lower bound, so you go L plus epsilon, and that is the difference. And once you get L plus epsilon, you can see that there will be an x naught in between. So let me write it down. The proof will be similar, so I will leave it as an exercise. There are right. So the infinitesimal characterization of the infimum. Okay, so this is how we write down the infinitesimal characterization of epsilon of infimum, or the epsilon characterization of the infimum. L is an infimum of S if and only if x is obviously greater or equal to L, because L should be the lower bound. And then for every epsilon positive, there exists an x naught such that x naught is smaller than L plus epsilon, right? So if you go epsilon above the infimum, then you will find at least one element which falls below that. Right? So the proof is similar. I will leave the proof as exercise, and so you can look it out and see how to prove it by using the same idea we did here for the upper bound. Right, so now we will go and do a little bit further on this completeness axiom that is about upper bound, sorry, the supremum and infimum. Right? Okay, so Yeah, I forgot to bounded below. I have to say. Then only you can say the infimum axis. I forgot to mention it is bounded below, but you should understand that now it is bounded below. Okay, so here's the problem and exercise. So this is again, you can consider this as one of the properties of suprema. Right? So you can see that you have a set, non-empty set S, subset of real number, and it is bounded above. So you know there exists supremum for the set, right? So that is obvious. Now for any real number A, so some arbitrary real number A, let us define a new set A plus S, right? So these elements in this set are of the form A plus X, such that X is a member of S, right? So all the elements of the form A plus X for all X in S. We have to show that A plus S is the supremum of that set is equal to A plus supremum of S. Right? So that's a different, that's what we have to prove here. Okay. So there are few things you have to do. First of all, you have to make sure that supremum for this set exists. Right? You only know supremum of S is there, right? Supremum of S exists, you know, but you don't know whether this set is the supremum of this set exists or not. So you have to first make sure that the supremum of the set A plus S exists, and then you have to prove that supremum of that A plus S is equal to A plus supremum of S. And so let us do that. So let me write down the solution. So clearly, right. So you all know that A plus S is a non-empty set because S is non-empty. A is any real number, so that set is obviously non-empty. And S is a subset of real number, A is a real number, so obviously A plus S is a subset of real number, right? And then you have to show that A plus S is bounded above, then only you can show the other way around, right? So to start with, but U is S is bounded above, so S has a supremum. Let us name that supremum as U. Right. So once you say that that is the supremum, then by the definition of supremum, you know it is an upper bound. So U is greater or equal to X for all X in S. Right. So that implies So that means when you add a with both sides, right? When you add a on both sides of the inequality, you get a plus x is less or equal to a plus u. Right? We can do that because of the order property which we studied earlier. Right. So that means every element in the set A plus S, right? You know that the set of elements in the set A plus S is of the form A plus X. So that means these are the elements in the set A plus S, and those are bounded by the value A plus U. Right? So clearly, the set A plus S is bounded above. So it is a non-empty set, it is a subset of real number, it is bounded above. So clearly you can say that it has a supremum, right? Right, so then clearly you know that the set A plus S has a supremum, right? And obviously you know A plus U is the upper bound of S, right? So now what we have to do is you have to show that it is the least upper bound, right? Right, so you clearly know that because A plus U is an upper bound of the set, right? So here you see that A plus U is the upper bound of that. So supremum is the least upper bound. So supremum is less or equal to A plus U, right? So you clearly know that. Right? So now what you have to do is you have to show that that is the least upper bound, right? Supremum of A plus S is less or equal to A plus U. So you have to show that it is the least upper bound, right? So right, so let's say V be any upper bound of the set, right? So of n plus n. Right, so let V be any other upper bound of the set A plus S, right? So then you clearly know by the definition of upper bound, A plus X is less or equal to B for all X in S, right? So you rearrange that. So if you rearrange this, what you have is X is less or equal to B minus A for all X in S. Okay, so okay, so B minus A is less or equal to S for all X in S, right? So if X is less or equal to B minus A for all X in S, then B minus A is an upper bound of S, right? B minus A is an upper bound of S, right? So if B minus A is upper bound of S, right? You notice that the supremum is U, right? But here you see that you define U as the supremum of S. But here what you get? B minus A is an upper bound of S. So clearly U should be the smallest upper bound or least upper bound. So U will be less or equal to B. So that clearly tells you A plus U is less or equal to B. Right? So in the B. Okay. So you see that A minus U is less or equal to B here. Right? You notice that A plus U is an upper bound and supremum of that is less or equal to A plus U. But any other upper bound B is this, right? So A plus S as supremum and A plus S is less or equal to U. That is the statement you have there. And now you take any upper bound, some other upper bound or some upper bound B of the set A plus S. And you see that A plus U is less or equal to B, right? So that means A plus U is smaller than all arbitrary upper bounds of the set A plus S, right? Because B is any arbitrary, so it is true for all. So that means A plus U is smaller than or equal to any other upper bound of the set A plus S. So clearly that should be less or equal to supremum of S. So now you have this inequality. This says supremum of A plus S is less or equal to A plus U. Here you have A plus U is less or equal to supremum of A plus S. If you combine both of them, and you see that both must be equal because you have A less or equal. So this value is less or equal to this value, and here you have the other way around. This value is less or equal to this value. So hence supremum of A plus S is equal to A plus U, but you know U is supremum of S. So it is A plus S. Okay, so this is how we show that the supremum of the set A plus S is actually equal to A plus supremum of S. So this is one of the properties of supremum, right? So I am writing everything as an exercise, but you can consider these as properties of supremum. Right? So this is one of the properties. Once you have a supremum of a set, when you add a real number with that, it is same as adding the real number to the supremum, right? So that's one of the properties. Okay, now let's do one another exercise. Now let us compare two sets, two non-empty sets of subset of real numbers, and then compare the supremum of those sets. Right. Right, so let A comma B be two non-empty subset of R such that A is a subset of B. Right, so you have two non-empty subsets and one is a subset of the other. So then okay, so then the supremum, note that supremum is a number, right? So it is a real number. So when you have real number, you have inequality, right? When you have sets, you have set inequalities, right? So the inequality means subset, right? So notation. But when it comes to supremum, it becomes number, so it's an inequality. But the order is the same, right? So smaller set has a smaller supremum, larger set has the larger supremum. And so you have to prove it. Right. So here, without loss of generality, let us assume that both of them, the supremum of both the sets exist, right? So otherwise, there is no point of talking about the supremum. So let us assume that the supremum of both the sets exist, right? So then U is equal to supremum of A and B is equal to supremum of B, right? Okay. So if this is true, then you see that small a is, let's say, equal to U or A. At the same time, small b is also equal to B or B. Right? So you notice that the definition of supremum, it serves as an upper bound. So U is A is, let's say, equal to U for all A, and B is, let's say, equal to B for all B. Right. But right, so this is the meaning of subset. Right, so you must have learned in A level or O levels, but just I wrote it down. If A is a subset of B, that means every element in A must be an element in B. Right? So if you take an A in A, then A should be in B as well, because A is completely contained inside B. Right? So because for every B in B, B is less or equal to B, but A is also a member of B for all A in A. So clearly A is less or equal to B for all A in A. Right? That means so because of that argument, we see that B becomes an upper bound of A, right? Because for every A in A is less or equal to B, so B should be an upper bound of A. But you already know U is the supremum of A. So supremum should be the least upper bound. B is an upper bound, but U is a supremum. Clearly, U must be less or equal to B. Right? So that is what we wanted to show. Supremum of A is less or equal to supremum of B. And so this is another property of supremum. Now let us finish it off with another property, right? Supremum. Right, so let us assume that a comma b be two subsets of real numbers and both of them are bounded above, right? We define also let the set a plus b as the set with elements a plus b where a belongs to a and b belongs to b. Right, so that okay. So we have to show that a plus b is a bounded above set, and we will show that, or we shall show that supremum of a plus b is equal to supremum of a plus supremum of b. Right. So let us start with the boundedness. Right. So clearly you know that for a in a and b is less or equal to supremum of b for b in b. Right. So you all know that because they say that the anonymity bounded above, so supremum exists and supremum are the upper bounds, right? So you all know that. So I am skipping writing all those lines and directly say supremum a is less or equal to supremum of a for every a in a, and b is less or equal to supremum of b for every b in b. Right? So if we combine both of them, a plus b is less or equal to supremum of a plus supremum of b for every A and B in B. And so you clearly understand this now, right? Because we have been writing this several times. A is less or equal to supremum of A and B is less or equal to supremum of B. So A plus B is less or equal to supremum of A plus supremum of B. So clearly you know that the set A plus B is bounded above, right? So I am skipping writing the lines again and again, but you know that A plus B is bounded above. Now we can prove the upper bound part, right? So that's right then. So let me. Okay, so from this line, you can say a lot of things. One is A plus B is bounded above. So if it is bounded above, and clearly you know it's all are non-empty, so supremum exists, and also by this you can say supremum of A plus supremum of B is the upper bound of the set A plus B. So supremum of that set should be the least upper bound. So supremum of A plus B must be less or equal to supremum of A plus supremum of B. Okay. So here you have an inequality, but you want to have equality. Right? The question says they want you to find equality. But here you have inequality. So let us show that the strict inequality is not true. Right? If the strict inequality is there, right? So if the strict inequality is there, right, then you can take epsilon as let's say this is positive, right? You know that because if the strict inequality is true, this one is positive, right? So let's say I will take this as 2 epsilon, right? Just for the sake of epsilon, let me take this as 2 epsilon, right? If epsilon is positive, 2 epsilon is positive. So there is no problem in taking this as a 2 epsilon, right? But you know, there exists A naught in A such that supremum of A minus epsilon is less than A naught. There exists B naught belongs to B such that supremum of B minus epsilon is less than B naught, right? So you know this because of the infinitesimal characterization of supremum, right? So you already know supremum of A exists. So if you go epsilon below the supremum, you get less than A naught for some A naught. At the same time, there will be some B naught for there and there. So if you add both of them, you get sup A plus sup B minus 2 epsilon is less than A naught plus B naught. Right? You have sup A plus sup B minus 2 epsilon is less than A naught plus B naught when you add both of them. Right? But you have 2 epsilon is equal to this to define this. Right? When you substitute this, you get sup A cancel, sup B cancel. Right? So basically, you get supremum of A plus B is less than A naught plus B naught, right? So I skip the substitution part, but you can substitute it and see this. Right? You put sup A plus sup B minus sup A plus B. Sorry. Right? So sup B here. Right? You can see that supremum of A plus B is less than A naught plus B naught. Right? That is not possible for a supremum, right? So supremum, you cannot have any number bigger than the supremum. And so this is a contradiction. I am using this notation to say that this is a contradiction. Right? If this is a contradiction, then your assumption is wrong. So equality false. Right? So I am skipping writing the few steps here, right? But you can understand now because we have done similar kind of exercises several times. So basically, because of this contradiction, this is not true. So obviously, equality holds, right? So that is how we prove the relationship between addition of two sets, right? The supremum of supremum when you add two sets. So that's all for the supremum, right? So I'm going to stop here, and in the next class, which will be tomorrow at 1, we will move away from supremum slightly a bit, and then we will talk about some special properties involving numbers known as Archimedean property. And so I will stop here and then do that tomorrow at 1.